Swayam Prabha. Digital India. Educated India.
That I missed, and I'm just showing it here, which is when we are using the nanoscale Syria on silica, you can see that you get nanoscale Syria particles mainly because they didn't show up in X-ray diffraction, but also when you were looking at the catalyst using Raman spectroscopy, in addition to the Raman bands of the bulk Syria, you could get a few additional Raman bands, very weak, which are associated with defects that are produced at the surface of nanoscale Syria particles. So Raman can also report on the presence of this. And actually you can see how the strong Raman band of Syria is almost missing and essentially replaced by bands associated with the highly defective Syria. So this is confirming this kind of a state. Now, Syria is a very interesting and versatile system. And what we have also been doing with Syria is to study its application for other reactions, mainly from the experience, because Syria is highly reactive oxide. The reactivity depends on many things, like the exposed phase it has, or many other variables. But it is also tuned by who you support at the surface of Syria. For instance, in the case of vanadium, basically what vanadium is doing is to make Syria a moderate combustion catalyst, moderate oxidation catalyst. Syria is running combustion, but vanadium Syria moderates it and then allows you that if you are flowing ethane on Syria, you get CO2, not a big deal. But if you flow ethane on vanadium Syria, then you are getting ethylene. So you are making it selective. But Syria is typically also highly reactive. So the other idea is to use an additive that will amplify its oxidation capacity, because that is also important. And this is a work that, again, we do in collaboration. This is always, you will always find the complementarity is a key pillar. So I always talk about operando, and a key message always is cooperando, cooperating, because in the end you collaborate with many people to do many things. And in this case, a student from mainland China, Qingyue Wang, was doing the thesis at Hong Kong University with Qin Yeong, and she came to our lab twice to study some samples of Syria that were prepared in a different manner. Basically, what Qingyue was doing is to prepare a cerium oxide of high area and modify it by adding vanadium and by adding gold. Why do I want to do that? Okay, because Syria has a big oxidation capacity. With gold, it will be an excellent combustion catalyst, and there is an application for that. With vanadium, it is a partial oxidation catalyst. So somehow it's like two additives that will make Syria selective oxidation and total oxidation. Selective oxidation was interesting if you want to make ethylene, but total oxidation is interesting if you want to work in combustion, for instance, of volatile organic components for indoor air quality. The same way that the other day we were telling about inactivating airborne pathogens, virus and bacteria by oxidative damage, killing virus and bacteria, we also want to decompose molecules, toluene, formaldehyde, many other chemicals which are in the air and that have to be removed. And for that reason, we were looking at these two systems. So Qingyue prepared these materials, and the nice thing is that the crystal size is around 10 to 13 nanometer, either if you verify by microscopy or by X-ray diffraction. But also the nice thing is that this series she prepared had a very similar surface area, 120 to 130 square meters per gram. And in addition, the porosity was also very similar, which is important because then the only difference between these three samples is the composition. With a similar texture, with a similar particle size, you are obtaining something that will behave differently, and it will be because it is a bare Syria, it has vanadium, or it has gold. And we were assessing the performance of this material for toluene combustion. Toluene is a representative volatile organic component for indoor air quality. So basically you are burning around 1000 ppm, because indoor air quality usually you are dealing with ppm concentrations of contaminants. The Raman and the operando Raman study shows you on the top part you have the activity. This is the bare area. It's converting CO2 quite okay. Converting toluene quite okay, mainly to CO2, but you also get the yields to carbon monoxide and to benzaldehyde. So it's not a complete combustion of the toluene molecule. Now, if you are adding vanadium, the system becomes less active because this is combustion. So the production of CO2 is even lower. You are increasing the benzaldehyde, which is more appropriate of a partial oxidation reaction. But in the case of gold, basically what happens is the conversion is much better, and the yield to CO2 is pretty much the same line than the conversion, is almost total selectivity to carbon dioxide, with a little bit of partial oxidation, but negligible. So gold makes it an excellent combustion catalyst, and vanadium makes it more for partial oxidation. You can look at the Raman bands and normalize to the intensity of Syria, which can be used like an internal standard. Then the spectra are vertically offset to see the details. This is giving a very qualitative image about the amount of carbon deposits molecules that accumulate at the surface of the catalyst during reaction. In a very qualitative manner, you can see that there are more carbon deposits on vanadium Syria than on Syria than on gold Syria. This is very qualitative. But what is more informative is at what temperature you are getting rid of these carbon deposits. I mean, if you look down here, you are getting rid of carbon deposits basically at about 300 degrees. On Syria, you are getting rid of the carbon deposit at about 250. And in gold Syria, you are getting rid of the carbon deposits at about 150. So there is a dramatic difference if you are getting rid of carbon deposits at the surface of this catalyst at 300, 250, or 150. It is not only that the total amount of carbon deposits qualitatively is bigger or smaller, is that if the surface gets clean at significantly, dramatically lower temperatures, this is telling you, wow, there is a major difference on the performance, and there is clearly a major difference about the nature of carbon deposits which are built up in the surface, which somehow correlate with what is happening in the reaction. So we can focus at different areas of the Raman spectra to find out what is happening, and then what we are observing, this is just a projection of the intensity of the hydrocarbons that we were running out of hydrocarbons at 300, 250, 150, but now we look at this box with lower frequency. The three catalysts present this band at 1160, which is typical of absorption of toluene on any configuration. So basically this band is not giving you much information about how toluene is absorbed, but it is telling you that yes, you have toluene absorbed in any form. Now, toluene may absorb in different manners. In the case of vanadium on Syria, you get this additional band here at about 790 that you do not observe on Syria or gold Syria, which is basically associated with the stretching vibration of the aromatic ring with the CH3 group of the toluene molecule. So that is a vibration that is not observed from the others, because the other two catalysts is presenting this other weak band over here, which is associated with the pi bonding of the aromatic ring, so that the aromatic ring is basically absorbing at the surface of the catalyst. And if the aromatic ring is absorbing at the surface of the catalyst, you are destabilizing this aromatic ring, which is already telling you that, okay, the most difficult part to burn in the toluene molecule is the aromatic ring, because this is very stable, and this pi bonding is already destabilizing it. So it makes sense that Syria and gold Syria are much more efficient burning toluene. And on the other hand, this binding that you observe on vanadium Syria, the aromatic ring is there, which makes it more stable. Also, if you look at the higher frequency, you see many, many bands. So you have a lot of hydrocarbons here. What are these? Well, it's basically a mare magnum of many things. And if any, there are two weak bands that show up in the vanadium that you don't see on the Syria or gold Syria, which is associated with carbanium species. Carbanium species typically formed by the absorption of toluene on Brensted acid sites like vanadium. So this is characteristic of the absorption of toluene on vanadium, which is actually the element that you have at the surface of this vanadia Syria. And these have more tendency of forming polyolefinic hydrocarbons, evolution more towards carbocations, and things that in the end up building up more carbon deposits that accumulate on the surface. And of course, these are more refractory. They take longer to be burnt away, and actually you need higher temperatures. So vanadia Syria is leading to this carbonium that make more complex structure on the surface, require a major effort for combustion, and then it is not a very good total oxidation catalyst, which doesn't happen on Syria and doesn't happen on gold Syria. And in the case of gold Syria, you even get rid of carbon deposits much sooner than on the other. So something is happening within the gold particles or within the gold Syria interface that is accounting for a much more efficient combustion of the toluene molecule. Now, there are several questions here. But, okay, we see that, but we still don't get the complete insight on the reaction. There is something that I also like to recall, because some years ago, before this work, we have seen how the vanadia Syria interface result in a very strong interaction. And you remember from before the coffee that cerium-3 is reduced at the interface with vanadium. And the Raman spectra during reaction is showing something there, hardly visible, which is the presence of superoxide species. Now, superoxide species typically happens when oxygen, molecular oxygen, absorbs on the effects of Syria at very low temperature. Because at high temperature, this oxygen absorbing with cerium-3 pass, it will reoxidize it, and then it will become lattice oxygen, oxide ion, and you no longer see the superoxide. So you never see superoxide at high temperatures. And in this case, we are observing superoxide at high temperatures. When you get rid of the hydrocarbon deposits, then you start to see that you have this superoxide at the surface. But that's normal because now we are dealing with a system that we already had discussed, which is vanadia Syria. And you remember that vanadia Syria resulted in a strong interaction that results in a very stable cerium-3 plus ion that you never reoxidize. So that's why even at 400 plus, you get superoxide species and they remain there because it cannot oxidize that cerium because of the neighboring vanadium. So that's why you get the superoxide, which is stable at 450, which usually people see it below 0 degrees. So that is also like another indirect evidence of the very strong stability of this cerium-3 at the interface, which is also interesting when you are doing studies to see that one study on something different validates things that you have seen from previous studies. That is also important to make sure of this consistency of data. But okay, let's go back to what we are now interested, which is the combustion of toluene on this material and how we can get understanding on the mechanism. Because we see a lot of changes in the hydrocarbon species. And I only told you, well, I get a little bit of carbonium, but there are many bands. Miguel, what's going on with this one? I say, I don't know. I cannot really tell because there are so many bands, so broad bands, which is like broad thing that you cannot really analyze. And to some point, it may not be that important for one reason that we will comment in a moment. We are also dealing not only with the hydrocarbon species, but also with the oxygen species. We have seen that vanadia Syria, at very high temperatures, you see the presence of superoxide species, which presence increases at high temperature once that the surface is rid of the hydrocarbons. But you know that this is basically telling you that it's not a reactive one, it stays there, nothing happens. However, Syria and gold Syria are showing the presence of peroxide species, which are more reactive, typically associated to the so-called reactive oxygen species. It's really something that you observe for Syria and gold Syria, and that can be associated with a much better combustion of toluene on these two catalysts. We wanted to maximize the activation of oxygen, to maximize the interaction of cerium with other elements, to see if we can create more defective Syria, reduced Syria at interfaces with metals, not only gold, but other metals, like for instance platinum, and see if we can get that. So we were working also on materials that are making like cerium oxide with the shape of a rod. And these are like, some of you were working with metallic organic frameworks. So basically we're using metallic organic framework, but as a precursor for an oxide. BCD is a benzyl dicarbonate. It's a very simple ligand. You make structures where you get this cerium benzyl dicarbonate, and we prepare it mixed with platinum precursor. And then when you make the calcination, this porous metallic organic framework goes into a porous oxide network, where you have the ceria closely interacting with platinum. And actually, when you characterize, you will see like these ceria nanorods, and these bright dots correspond to the platinum nanoparticles. And you can even look how there is an interface between the platinum nanoparticle, about 2-3 nanometer, and the ceria nanorods. And you can see these locations and changes just at the interface between the platinum and the cerium. And that will typically generate defects or reactive sites. And you have a very big dispersion of exposure and interaction between the platinum and the cerium. And actually, in the precursor, the cerium is essentially metallic with a little bit of platinum 2 and hardly anything of platinum 4. But upon calcination, what happens is that the platinum has a strong interaction and it is more oxidized. It is essentially platinum 2 plus with a little bit of metallic and platinum 4 plus, but clearly is more oxidized than before. And in the case of cerium, of course, it was a ligand compound with a big fraction of cerium 3 plus, and now it has a lower fraction of 3 plus and 4 plus. So basically, this is the cerium oxide with some reduced sites. So you have burned away the organic ligands and you have a mixed porous oxide with big interfaces between platinum and cerium. And we are using this also for the combustion of toluene. And the performance of this material is very good. You can actually observe how this platinum at the benzyl dicarbonate oxide that derives from this benzyl dicarbonate metal organic framework is converting toluene very efficiently to CO2, already even at 200 degrees C and above. If you only use the nanorod that derives from this MOF, you also get quite a good performance, but not that good. I mean, you have to go close to 300 to be able to get a total combustion, which is telling you that indeed the interface between platinum and cerium is really promoting something special on the system. You can synthesize conventional nanorods that do not come from metal organic frameworks with or without cerium, and their performance is not that good, particularly below 200. So this system is particularly efficient, and we want to know why. Of course, because of very close interaction between platinum and cerium, and also keep perspective that the industrial catalysts are good above 300 degrees, and here we're getting very nice results at 200 plus and above, which is very attractive. And if you look, for instance, at the system working at 150, you can see that it's a dramatic difference already, like 60 against something like 40% conversion of toluene into the carbon dioxide. Operando Raman studies again shows us like big amount of hydrocarbon species at the surface. As you increase temperature, you get rid of them. But the most interesting part is here when it comes to the oxide species, the peroxide species. So you can see that in the case of ceria nanorods that derive from benzyl dicarbonate, basically you have this vibration at about 830, which is typical from peroxides sitting on a given site. So that basically you get the peroxide species like this, sitting on a given site. So this is like 830 wave number. But in the case of platinum cerium, you observe two, the same one, 830 on a single site, or another one at 860, which is basically attached to nearby vacancy. So in the end, it's a peroxide, but it's binding together or it's binding in two sites. And the 860 is more reactive. You see that it is consumed before, and then you still have 830 that remains for a little bit longer. They are weak, but they are there. And basically, the presence of this 860 is accounting for the reactivity of the system in this temperature range at about 450 and below, where basically you didn't have any reactivity here, but you do have in platinum. And well, basically that was telling you how important it is. The reduction of cerium also fostering not only random defects here and there on cerium, but because of the interface you have like more line defects, and these line defects allow peroxide binding on these two sites. It results in a more efficient activation of the peroxide than when it is on a single site. Now the idea is, because this is working very nicely, can we use other metals that are more economic to activate and to amplify this oxidation capacity of cerium? And then we were looking at copper, which maybe is probably a very convenient element, very good for combustion, and much more economic. And in this case, we were also using another benzyl dicarbonate precursor. Then we were getting platelets like this. So here you have the element composition from the electron microscopy. You see that basically, there is no silicon there, but we do have ceria before and after the combustion of the MOF. You also have copper, and the allocation, well, appears to be pretty random, so that should be like a good interaction between the copper and the ceria. Of course, oxygen, after the combustion, you still have oxygen, and all the carbon and all the organic part of the MOF was burnt away, because it is an organic ligand, so you burn it away, and there is no longer organic part. That makes sense, because you are making a porous oxide out of a metal organic framework component. And the way it looks like is like that. You see like big amount of crystallites. If you look more into detail, you see like different kind of domains. Some of them correspond to ceria, some of them correspond to copper, and then you get these kind of mismatches between the lattices, which ultimately foster the creation of defective cerium sites at the interface between cerium and copper. Like over here is even more apparent. So basically, the synthesis is something like this material, and then you make a combustion to get this mixed oxide with a deep entanglement between the copper and the ceria. So this is before, and this is after combustion. When do you get the optimum mixed oxide? Well, you have to do several calcinations, and for instance, in our case, the optimum calcination temperature to get these porous oxides was about 400 degrees centigrade. I mean, if you were doing combustion of this material at 375, surface area was 6 square meters per gram, which is not that much. 600 degrees C, the area decreases to 70, which is not okay, but if you have 400, it's 100 plus square meters per gram, which is very nice. So basically, our combustion was made at 400, where you have a maximum area, and also you minimize sintering phenomena that will result at higher temperature, in a better crystalline defines, less defects and less reactivity, or in complete combustion like it happens at the lower temperatures. And even the characterization of the system, when you are looking at both the Raman and the X-ray diffraction, well, X-ray diffraction, reference ceria looks like that, reference copper looks like that, and this oxide generated by the composition of the MOF looks like this. So you have some bands, you see some distortion, and it's essentially it looks like ceria, but there is some distortion. And you may think that this is probably one peak from copper, but very small domains, highly amorphous. Raman will report on these materials, mainly about the ceria. This is the reference Raman band for pure ceria. This is for pure copper, with these bands around 200 plus to 300, which are apparent here, and at essentially the same position, but the most interesting is that in the case of cerium, you get significant distortion, a significant change on this major vibration of ceria. 15 centimeters to the minus 1 shift in the Raman shift is quite a bit. So this is really telling you that you are getting a highly distorted, highly defected ceria, which actually it is closely entangled with copper, and which accounts for an efficient activation of molecules. And actually, when you're looking at the performance of this material, you are getting very good conversion for the combustion of toluene. Here you are comparing this metal organic framework derived material against the same material without copper, and again you see a significant increase in performance. And also down here you have a comparison with only copper oxide. All of them are active, all of them behave well, but the mixed system behaves significantly well, and we are talking here about some 50 degrees better, which is a lot. The performance of this material was tested not only for toluene, but also for other volatile organics like toluene, xylene, acetone, and methanol. And then the nice thing is it behaves well for toluene, but also for octylxylene, acetone, or methanol, which are like other representative volatile organic contaminants. So, but the question that I have not answered yet, and that you are demanding me with anxiety, is what happens with the hydrocarbons? And I look at these bands, I say, wow, this is very difficult. We have to tell apart the reactive pieces from the other pieces, and that's difficult to handle. So one option is, okay, let's try to get complementary insight, infrared, and look at Raman and look at infrared and try to see if we can explain something. So we were doing this collaboration also with a group in Argentina, in Santa Fe, the group of Sebastian Collins, and over there, what we were observing is that when you are absorbing toluene, which you have the molecule here, on Syria, one of the first things that you start to observe is the formation of alkoxide species, Indian carbon oxygen cerium bonds. So these kind of absorption molecules. And we wanted to observe, here you see how they develop from here. Now, we wanted to observe what is happening there. How does toluene absorb at the surface of this material? Computational chemistry is telling you that it will absorb through this carbon. Okay, fine, we know that. We have observed that the Raman spectra is also telling that. And the infrared is consistent with this. But how does it behave? Mainly if we use other things like gold, where we are changing that interaction. The infrared can give you very fast and very good signal about what is happening. This is the CH region of the toluene molecule. So when you are absorbing toluene at the surface of gold Syria, you see how here you have the infrared band of aromatic CH, which is the toluene, but very quickly, in a few minutes, you start to see the development of benzoate, which is already a more oxidized molecule that derives from the oxidation of toluene. And the interesting thing is that you are absorbing toluene at the surface of gold at 200 degrees C without oxygen. So this is already because of the lattice reactivity, it is already converting the toluene into benzoate. Also here, when you are absorbing, you start to see all these bands that correspond to benzoate, carbonate, and formate. These bands look very different than the Raman, because Raman is looking more at polyolefinic carbon deposits, and infrared is more sensitive to oxygen-containing deposits. Which one is true? Both of them, because each technique is looking at what they better measure. Now, in the case of Raman, the infrared, we already made a more detailed study, and then we were comparing the same thing. What happens if I feed toluene to the Vanadia Syria, which is the less reactive one? Well, in this case, when you absorb toluene, basically you observe that this region here of the CH, of the absorbed hydrocarbon, remains like that, and you hardly get any oxidation to the benzoate. And down here you absorb toluene, and what you observe is toluene, more and more and more toluene at the surface of this material. If you compare gold and vanadium, you see, you absorb toluene on Syria, on Vanadia Syria, and you get toluene, more toluene, but basically toluene. You absorb toluene on gold Syria, and you immediately get oxygenates, like toluene, benzoate, formate, carbonates, big mess of things together, which is absolutely consistent with the CH region, where you see the evolution that is very, very limited for Vanadia Syria, where basically you get the aromatic CH and very little of the benzoate. However, when you're absorbing on gold Syria, very quickly, and this is like 5 minutes, at 200, everything goes in essentially to the benzoate. So you see changes on the benzoate, you see changes here, so there is clearly oxidation without oxygen, 200 degrees C. Okay, what happens if I flow toluene and oxygen on this catalyst at the infrared operando system? Well, in the presence of oxygen, what happens is like a Syria catalyst, for instance, you flow through it and you see something. You see like there is an absorption here that goes into another intermediate and then goes into that one. And you see the development of other bands here. So if you integrate the bands, basically what you observe is that the toluene within a minute starts to be consumed. Within the minute, you start to see like benzyl oxide, which is this alkoxide that is being formed and then goes through a maximum and disappears because you start to get the formation of formate species. So you are starting to oxidize the material. So in the presence of oxygen, Syria is reacting faster. But you can still see the transition. Within these 50, 60 seconds, you see things changing. Now, you go to the crazy burning gold Syria, and then things look different because you see a lot of bands changing very quickly. If you look for the characteristic bands, what you observe is that as of time 0, you no longer see the bands of toluene. So toluene lands and boom, no, because of the shock. Like, it completely goes into something else. You can hardly see the toluene. You already start to see how you get benzoates, and these benzoates are readily being consumed. and going into formates and other kind of oxidation products. And this, remember us of what we said yesterday. How can I see what is happening here? How can I understand what is happening if this is very fast? And how can I tell apart all the bands that come from spectators and concentrate only on this part? Because you, watching a movie, you will tell that. But as an spectrometer, you are not able. You will not discriminate from the signal of the spectator, from the signal of this poison, from the signal of the active site, from the signal of the reactive molecule. So you have to do something to discriminate those things. I'm going to comment a little bit of modulation, but you will develop in more detail. But here you have I think this is good because you will see one example with a very general comment, and you will probably elaborate a lot more on the technique, and then you will remember this. What is the idea of how to resolve things? I don't know if the approach is known to you, but it's something very interesting. If you make a periodic perturbation to a system with the frequency and with the time that is relevant to the reaction time response, you will be able to perturbate the system and then observe a response of the system. So like you do something like that, and then the system will respond something like that. There is a little bit delay because you do it now, and within a fraction of a second, the same thing will happen there. But the important thing is not that they are simultaneous, because they're not really simultaneous. They are slightly decoupled in time. But if you do something like that, it will do something like that. So you make a perturbation, and there will be a response to that perturbation. Now, this is the idea of the modulation excitation spectroscopy. You make an excitation modulated. Typically, when you think of a modulation, you think of a sinusoidal wave, but any kind of perturbation is good. So the idea is that when you do that, when you make a perturbation, the system is responding. And of course, how is the system responding? You are making operando study, and everything changes. You get the bands from the spectators. So you are doing something, most of the spectators are like that. But you're doing something, and the active side, you're doing like that, like that, like that. And so the active side is, okay. So there is a response. And the rest of the people, looking, he's putting the eyes in his finger, or the finger in his eyes. But it's just spectators. They're not really reacting. It's not like the active side, which is being totally perturbed. And there is so if you could somehow tell apart who is responding to your perturbation and who is not responding to the perturbation, you can cancel out those who are simply like, you see, that's funny. And see only the signal of those responding to the perturbation. Now, this is conceptual. Mathematically, maybe not that simple, but in the end, what happens is what you see here, that all this crowd, which is looking at it, doesn't really respond. I mean, they are responding more or less, but not with the same frequency of the perturbation. So they will be cancelled out. And all these signals from all these things here are killed. But here you have something that is responding. So the perturbation, you increase and decrease or whatever, you do something. So in the end, these bands will increase and decrease. And that is the only thing that you will see. Bands that appear and disappear. So basically, when you make this conversion, what you see is something like that. Spectators are already taken away. And the active phase goes up and down. I don't know if the politicians do the same thing here, but in Spain, politicians tell to the people in the party, if you don't move, you won't be in the photo. And the people who obey and comply stay in the photo. And those who have initiative, out. Here is on the way around. If you don't move, you are out of the photo. So you will only see the active guys, the people who respond to this stimulus. And that works in an interesting manner, because here we are talking about phase domain and time domain. What do I mean by that? Well, what I mean by that is that when you are making a perturbation, imagine like a sinusoidal perturbation like this, and actually this is like 1, 3, 6, whatever seconds. Okay, but here or here is the same. I mean, once that you are here, you are beginning again, and here again and again, because it is periodic. So the unit, periodic unit that is being repeated is this one. So actually, when you are going here, here, and here, it is the same than here, here, and here. Agree? Okay, so because this is something periodic, you typically think of something periodic like a loop, like you are making a loop in your life. So it's something cyclic. So you can say 1 second, 3 seconds, 6 seconds, 9 seconds, 12 seconds. You may say that, but it is the same. And in the end, what you're doing is that you're doing this at 0 degrees, 90 degrees, 270 degrees, 180 degrees, 270 degrees, 360 degrees. And again 0 degrees, 1 degree, 2 degrees, because this is a cycle. And actually, you don't really care about that, because you will make it ad infinitum and you can be looking at this, or at that. So the time is no longer important. The time domain, they say, philosophers say that the time is an illusion. Well, maybe, but here time is irrelevant. What is important is the phase. The phase is basically this moment here, or here, or here. In any case, this is the same moment. This is the same phase, because what you're doing there is here. And you always go back to this point. So in the end, what you do is that you don't present a never-ending story, but a cyclic story that begins with 0 degrees and ends with 360 degrees, because this point is already this one. And because you're doing a periodic perturbation, and in your analysis you're getting a periodic response. So what you do regularly will also happen regularly in your sample. This is important. You got this point? Okay. So what we did is a collaboration. And again, the complementarity is important. We make Raman, Hong Kong made excellent synthesis, Argentina, they're very good at modulation with infrared. So collaboration is, and by the way, we are right more or less here. So even in the drawing, I already found out a connection with Madras. Okay, how do you do this perturbation? Mathematically, this is the typical perturbation that they do. But even if you make a square wave perturbation, that can be assimilated in all the process to the other thing. And that's very convenient, because making a square wave perturbation is very convenient. If you have a four-way valve, where you have a flow with a reaction feed, which for instance can be toluene plus oxygen plus nitrogen, like 1000 ppm of toluene. And then you have another flow which is only oxygen and nitrogen. With a four-way valve, you are feeding this to the operando reactor, and you are feeding this to the exhaust. And you are periodically switching. So you are feeding, and here is the reactor. So basically, by switching this periodically, you are feeding toluene, oxygen, the air with toluene or without toluene, with toluene, without toluene, with toluene, without toluene. So you make this perturbation, which is toluene, no toluene, toluene, no toluene, toluene, no toluene, and continuously air. This is a periodic perturbation. What is the frequency of this cycle? Well, you have to find out. Depends on how the system is responding, but basically this is what it is. So basically you use this kind of automatic valves where you establish the frequency and you do that. And you can do it with an infrared cell, a Raman cell, or whatever, and monitor what is happening. You measure online with mass spectrometry, and you measure the activity, and you measure with the spectrometer what is happening on the sample. And this is what we get. But this is time domain. So you see something, if you have a very good eye, and you look here, maybe you see, oh, yes, something is changing around it, but the main peak is essentially there, but there is something here, something here. So that is the big challenge. How can I see that? Well, then you have the mathematical procedure that will take the time domain into the phase domain. And the phase domain looks like psychedelic. No, they didn't put anything in your coffee. It is like that. But what do you get here? Well, you are getting not many bands, but the bands that change, the bands that are associated with reactive things that are happening. You get positive and negative, yeah, because during the cycle, sometimes you are feeding toluene, and when you feed toluene, maybe hydrocarbon species will increase. And then you stop toluene, and then the hydrocarbon species will decrease. So you will see that sometimes the intensities are growing, and sometimes the intensities are decreasing. But any molecule doesn't have one band, it has like 2 or 3 bands that go up, or 2 or 3 bands that go down. And this is basically what you see here. A little bit of a chaos with a lot of bands going up and down. But you also see that at these are like at a few representative moments of the phase, like here, 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 because that can be almost a continuous. But what you see that sometimes these two bands grow, and more or less these two bands grow at the same time. And later on you get this band that is growing, but independent to that one. So even if you look here, you can say that these two bands here belong to one species, and that belongs to another species that are actually evolving at different moments. Now, trying to look at this, after a while you go dizzy, and you cannot really tell anything that I need an aspirin or something like that. And then you have to do something. So yeah, this is the phase domain, but in the end you have to analyze, because each molecule we have not only one, but several. And in the end what you have there is a linear combination of many spectra, positive and negative. And then you have to find out what it is. So you go to all classical mathematics, all these multivariate curve resolution, alternating least square, all these things that are automatically done, and in this paper they tell you how to do it, for instance, where basically you can tell apart the components, and then you go from this messy thing down here. So you are making the experiment. You go from the phase-sensitive domain, which is go into this, which looks nice, but you want information. You don't want something that looks beautiful and you can put a pattern in a sari, or no, you need something else. Then you have to get from there into the components and to see whether these components are being created or destroyed. And then, after you do that, you can tell all the components apart. So you also can represent this psychedelic drawing like something like a two-dimensional plot, where the red things will be positive peaks and the blue things will negative peaks, or vice versa, whatever. So then you are doing the reaction with toluene, and then you see that here in red these bands are increasing, that band was decreased and increases later on, and this is the phase. So basically during half of the cycle you are feeding toluene and air, or during the other half of the cycle you only feed air. And because this is a cycle, after this moment, this is not the end. This continues here, because basically you are just doing a cycle. So this peak that starts to grow here is that further grows there. So it's like if you make a scroll, and if you wrote everything around it and you get something like this and you put it like this, if you do like that, it's like a never-ending story, because it's absolutely reproducible. So think of it like a circle. And think of it like from 0 degrees to 660 degrees. So basically you are getting a continuous analysis of it. Actually, in Madrid they have one of these printed as a roll, and it's like a tube. And I think I spin it like this because it's very nice. But you can imagine, I should have brought it with me or print it out here. But you can imagine that. So basically you see that how this is a completely cyclic process. You see that some bands are formed here when you are feeding toluene. Other bands form here when you are removing the toluene and only air remains. And you can also see like this band, this and this band and this band and this band pretty much grow up at the same time and decrease at the same time. So they are in phase, which probably means that either or two molecules happen at the same time, or very likely is one molecule which is going through a maximum at that moment, or bands that are being consumed at the same moment, like this, or this, and this is decreasing. So you can always tell things apart at a given moment in time. And then, because of the MCR analysis, you can also identify who is being formed and who is being destroyed, and then you can see like a number of components from this spectrum, like if you cut here or here or here, and you make just a plot of selected moments of the phase, selective angles of the phase. For instance, here you get 360, 300, 250, 200 degrees of angle of the phase. So you see that sometimes some bands are like this benzyloxy, which is being formed, decreases, and is being consumed here. So benzyloxy forms when you are feeding the toluene, goes through a maximum, start to decrease, and then when you cut the toluene off, then it decreases, and then when you start to feed the toluene, it starts to grow. And the same thing is happening with this species. It's being consumed, and then it's being developed, and it's being consumed. And then you can start looking at things, and you can see like this is benzyloxy, these are bands associated with benzoates, these are bands associated with aldehydes. And sometimes this is the most important thing from modulation excitation. It's not only what you see, but also what you don't see. Because before we have many infrared bands. Now, of all these infrared bands, many of them are gone because they didn't respond to the periodic perturbation. So these are things, debris, residual molecules that accumulate on the surface, but they are not directly involved in the catalytic cycle. They are more like byproducts. So all these bands disappear. And now all what you see is those actively responding. So the first thing that you see important is what you don't see. You get rid of the spectators. And then you can analyze which one is growing and which one is decreasing. And to us this was important because we couldn't see what was the key intermediate going from the toluene to the CO2. And then we start things that were absolutely not apparent in the spectra, infrared or Raman. The presence of aldehydes, that was not apparent. And we saw a lot of bands over there that increase synchronally when you are at this moment. And basically, were like conjugated aldehydes, partially oxidized, unsaturated compounds, crotonaldehyde, probably maleic anhydride, butanone, many compounds associated with the combustion that you can see now and before were totally covered because of much stronger bands of spectators. And if that was for the Syria, in the case of vanadium Syria, which is slower, like for instance here, you can see the vanadil mode. The vanadil group, you see it decreasing, goes negative when you are feeding the toluene, and then when you take the toluene off, you see it being reoxidized. So this is like the vanadil group, but also you can see like a CO species over carbonyl species from the oxidation. So you can see a lot of things coming in and out. Even the formation of CO2 is relevant because atmospheric CO2 that you get in the infrared spectra doesn't respond to your perturbation. So the CO2 that grows and decreases here is the one that grows and decreases with your perturbation. So this CO2 is part of the reaction. It's not environmental CO2, which is also important. And with gold Syria, it's very fast. It's a crazy burning system. So immediately you get a lot of water, and this is not environmental water. It's water that is being formed or consumed, C positive or negative, during the reaction. And so as you see, like a lot of CO2 and water form, because if this is formed from the reaction, then you no longer feed toluene and you feed the oxygen, and then the production of water and CO2 decreases and then increases. But you still see like a little bit bands of formates and other molecules which are being formed, or even the benzyl oxide. The first molecule is formed and very quickly consumed. So you get a lot of insight into the reaction mechanism. And again, because you're doing the perturbation and because you are going into the phase domain. So then you can go into the reaction mechanism, you can see how the toluene is absorbing, basically get insight at this moment where the aromatic ring is being broken and ultimately decomposed into the carbonates and formates, this kind of species which are being formed at this transition period. And this is the insight which are still under progress and under analysis on these systems. And we're also doing a similar analysis with Raman, which is much more sensitive to the response to peroxides and superoxide species. And this is actually like ongoing projects. So if I pay a visit and whatever, and I give an invited seminar, you will come running to hear my seminar, and then I can tell you what is the outcome of the story that we are making with the Raman and with the oxygen species through the same methodology. And in general, I told you, Syria is very special. You can modulate the performance of Syria. Syria can be nanorods, can be nanocubes, can be nano-octahedra. So the exposed phase of Syria can be very different, like you see here. And you can do refaceting with temperature treatment and with many conditions. So all kind of different Syria will have different kind of reactivity, different kind of sites. And that is also a way of tuning performance. And here, for instance, you can observe how the absorption of oxygen doesn't result in the same kind of species. This is a work made by Chile Wu and Steve Overbury from Oak Ridge National Lab about how you are getting these peroxide species, and it's not the same depending on the temperature on nanorods or on nanocubes or nano-octahedra. So in nano-octahedra, for instance, you don't get the peroxide species. You do get some of them on the nanocubes, which have some reactivity, on nanorods where they have more reactivity. So these things already happen by shaping up how you make the Syria nanoparticles. If you're adding an element, you also have some saying, some impact on these kind of things. And then you can get like different kind of reactivities just by modifying the Syria. Even if you make a methanol TPSR, the reactivity profile is completely different, whether you are looking at the rod, cubes, or octahedra. Just imagine adding it to other elements. Going back to my other interest, which is about the toxicity of nanoparticles, Syria is also very much studies in toxicity of nanoparticles. And Ushi Graham in Kentucky made a very nice work about how the oxidation state changes for supported for Syria nanoparticles in the spleen, over here in the body. And basically, through time, what she was reporting is that Syria nanoparticles get little by little reduced in the body. You remember these kind of shapes, like the one we were looking at for the operando Vanadia Syria? Well, the same thing is also reporting how the Syria is evolving in the body of a person, or actually of a rat. They were doing it with rats, not with people. I don't want to get her into problems. And basically, it was showing this kind of reduction of the serum, similar to what we were observing here, but in this case, because of the interaction with the spleen. Now, what is happening? That the serum in the body is getting continuously reduced because it is oxidizing the environment. But because inside the body, you also the supply of oxygen can be limited here and there, little by little, serum is making an oxidative stress damage, but then it's been reduced until it's no longer making a damage. And then you can also see this evolution, because at the beginning it is being reduced because it's oxidizing the environment until it levels off. Many things can change. When you want to make Syria for some industrial application, they are increasingly asking from the authorities, okay, make something that if there is a release, if people is exposed, you are also aware that it will not have an impact in the health of the people or in the health of the environment, which sometimes is impossible because functional material has a given property. But these kind of studies are considered, and so somehow in the end, health, catalysis, energy, environment, and everything connects, and one of the major connectors is actually the spectroscopy and the catalysis. I wanted to complement your story on the work by Carlos Ortiz, who was a postdoc in our group, with the sodium modified tungstate along with the role of manganese. So basically, that's just already very quick because we are approaching the end and we have to give some time for questions. But basically, we are dealing with a system where we have different additives. And we make, in the case of silica-supported sodium tungstate modified with manganese, you may have multiple scenarios. At low loading, tungsten or wolfram will be dispersed at the surface of the silica support. If you go to the monolayer, you will get BO3 crystallites. And if you are adding sodium from very low loading, there will always be an affinity between tungsten and sodium. And also the environment changes because the dispersed tungsten will be like, mainly can be tetrahedral or tetrahedral when it is dispersed, octahedral when it is crystalline, and then tetrahedral again when it has sodium and it goes into the different kind of tungstates. So you can get already information from these kind of cases. These, you already saw it yesterday. Interesting point is that above given temperature, you no longer get diffraction patterns of the sodium tungstate because it's molten. Then it is a liquid phase, and it is the one working on this reaction. You put manganese, and at the moment at which things melt, change, but anyhow, it's like 50 degrees higher or above. When you are up there, everything gets molten. If you look at it with Raman, you can also see similar story. You are hitting the tungsten on silica. Here you have basically that you get the gamma phase of a tungsten oxide that goes into the beta phase and into the alpha phase. That's it, because this is only tungsten on silica, so nothing else happens. Now, if you have sodium, now you don't have only tungsten oxide, which was these bands here, but new bands, which are associated with tungsten, sodium tungstate. So, well, in Spain we say wolframate, because W actually is from wolfram, wolframio, and tungstate is always like a weird word to me. And anyhow, the tungstate. So basically, as you increase temperature, what you are observing is that you also see changes. You are going from a cubic tungstate to an orthorhombic one, and then it melts. When it melts, you still see it in Raman, that you cannot see it in X-ray diffraction, but you see things, and even sometimes you get very strange things coming out from here on the spectra. So something else is happening on the sample, because this broadband is not from the sodium tungstate. This is another story that happens on the sample, on the support. But we see it in a moment. And if you also have manganese, in addition to that, the pattern is very similar. You go from cubic to orthorhombic and molten, but the temperature at which you go from the orthorhombic to molten changes when you are adding manganese to this sodium tungstate. If you look at the Raman spectra in detail, what you are observing is that many things are happening there, and you can observe like the evolution of the Raman bands. Like you see the sodium tungstate goes from cubic to orthorhombic and finally melts, or the silica support, which is an alpha cristobalite, you see how it is progressively changing, and then all of a sudden there is a crystalline change phase. Here you have how you are going from alpha to beta cristobalite crystalline phase on the silica, which accounts for this very broad change from the, which is based mainly because of this change on the silica support, which maybe you couldn't report from X-ray, but you can from the Raman. And then you see this broad pattern over there. You can integrate the different components and analyze the evolution of the different phase with Raman spectra during all this temperature treatment. So you see how there is a progressive decrease of the cubic sodium tungstate phase, which in the end is replaced by the orthorhombic sodium tungstate, and also at the given temperature, the disappearance of the alpha cristobalite silica phase and the beta cristobalite. So you can monitor all these things. Here you have it for the manganese sodium tungstate with all the phases, including, for instance, this beta cristobalite, which is a broadband. And then you can see the evolution and the changes with different temperatures and different compositions. Here, for instance, you have on the left without and on the right with manganese. So things may look alike, but you can see, for instance, the moment at which you decrease the cubic sodium tungstate compared to the dominance of the orthorhombic one, compared what you observe here. So things, relative population are changing, and this is also associated with a better performance of the catalyst. Actually, the manganese promoted sodium tungstate silicon is much better than the one without manganese. But whatever. So for today, this is it. We have still 10 minutes for questions, and tomorrow we will continue. Questions, I mean.
This one, the tungsten oxides we have. So existing the two symmetries, for example, tetragonal and we say octagonal. But moment when you add the sodium into that, octagonal phase was, I mean, the tetragonal phase was stabilized.
Yeah, but because you get the tungstates that have a tetragonal environment, a tetrahedral environment.
So what is the role of sodium so that it stabilizes the tetragonal, not the octagonal?
Well, in the absence of sodiums, basically you are dealing with the bulk L012. And that system is not performing well in the system. You need the presence of sodium, and you need the presence of manganese, and then there is also, the manganese also has an importance regarding the oxidation state in addition to the structural things. So basically what we're observing here is how different phases evolve with temperature in the phase of different heating temperatures, where you're looking at that. And then you can see structural changes and how these correlate with the performance of this material for the conversion of C1 molecule. Questions, concerns, modulation, Raman, operando things. One thing that you have seen that is always very important is the complementarity. Today, we have been jumping from Raman to infrared to computational to in situ things sometimes, then back to EPR, then back to, I mean, we are playing with a lot of techniques, with a lot of measurements at the same time. And this is something that goes to the paradigm of the beginning when a lot of wise people are looking at an elephant. If you only get the information from one of these wise persons, you can have a very accurate description, but maybe wrong. And if you look at different descriptions from different techniques, and in addition, you make them under real working conditions, everything will be a lot more informative, because it's not the same to study the skeleton of an elephant and a living elephant. So that living elephant will be the operando study. So then you are looking at this living elephant, but you are looking at this living elephant with many complementary techniques. And that is fundamental if you really want to tackle things. And the other key message in the case of operando, by measuring simultaneously what happens with the structure, with the performance, you can connect things. You can sometimes see how, okay, you build up a vanadium antimonate, and then the catalyst is active for propane oxidation. Or you can see that the formation of cerium vanadate is not per se killing the catalyst, but a more extensive one, which gives a second reading. This bridging oxygen between vanadium and cerium is the active site. And then you have to corral the reality to say, okay, how can I get to see that? I make operando synchrotron, but I see very nicely vanadium, I cannot see much of cerium. I make nanoparticles and then I can see cerium nicely. I make computational chemistry to understand what is happening there. I do complementary studies. Even the group of Sauer, they were also doing atomic force microscopy and scanning tunneling microscopy to assess the interaction between vanadium and cerium. So then you end up doing a lot of complementary studies to describe what is happening there. And then you are looking at the hydrocarbon species, at the oxygen species, and you have to tell apart which one are spectators, which one are active ones, and that requires like some kind of dynamic system. Some dynamic systems, like for instance steady state isotopic transient kinetic, was an approach where basically you have a reaction, and in the steady state isotopic transient kinetic, what you do is not on and off, is that you have maybe toluene on both sides, but here you have toluene with carbon-13, and here you have toluene with carbon-12. So what happens is that by doing the switch, and you make one switch, the reaction is exactly the same. Actually, the reaction is not even aware that you have made a change, but then all of a sudden, one of the molecules comes with a different isotope. And then with spectroscopy, you will observe things that are telling you which is more an active species, which is not. So this kind of, and I don't know if you will talk about Sitka. Probably not, a little bit. So this is like one pulse, basically. You are flowing, everything gets a steady state, and then you switch and see what happens. Another way of doing things is the periodic modulation, where basically you do something periodic. You could make that. You could make two isotopes also. You could make anything, because the perturbation can be anything. I told you, like, toluene, not toluene, okay. But the perturbation could be photocatalysis, and could be like light on, light off, light on, light off, light on, light off, and that will be also a modulation. Or you can be working with a system that you can quickly put high pressure, low pressure, high pressure, low pressure. You can do that, and you're doing a modulation. Or, for instance, a very elegant work is solid-liquid interface. You are doing catalysis, and you want to look what is happening at the surface of the catalyst where the molecules absorb. And then, for instance, there was a very nice work by a group of Davide Ferri at the Paul Scherrer Institute, the one who made this coffee machine, basically doing a polarization modulation, so that the light, he was making infrared with polarized light. Why? Because when the molecule is absorbing on the surface, if the molecule vibrates like this, and it absorbs, these vibrations will remain, more or less. But vibration like this, no, they are stopped. So by absorbing on the surface, some of the vibrations are affected. So you get some polarized signal coming out of the surface. So what you are doing by polarizing the light is that you are getting signals that come from the surface and from the liquid, and signals that only come from the liquid. Because the liquid is absolutely random, and if you polarize the light, it has no effect. But the signal from the surface, depending on which polarization you have, you can see or you cannot see the signal of the molecules absorbing the surface. So by doing that, all of a sudden you kill all the signals from the liquid phase, and you only see the signal of the molecules at the surface. And then you can make a mechanistic study of what is happening at the surface of the interface between a solid and a liquid, getting rid of all the signal of the liquid phase. Looks like magic. It's not magic, it's technology. But of course they say that technology is never sufficient advanced until it cannot be distinguished from magic. And in this case, it's pretty much something like that. Okay, so